Good day. My name is Jomar Fellores, here with my members Radzie R. Bagallon, John Bernard B. Barce, Louise Gabrielle B. Nase, and Cyril Vinuya. Here to present our project, Optimizing Elevator Allocation in Multi-Story Buildings, an agent-based simulation for Mapua University, Makati. This report will have 7 sections.
Let us begin with our background and motivation for a study. Elevator systems are absolutely vital in modern multi-story buildings, playing a crucial role in both operational efficiency and the overall user experience. This is especially true in dynamic high-traffic environments like university campuses. However, a common challenge is that these systems often perform suboptimally under fluctuating demand. Think about busy peak hours, class changes in between schedules, or special events that lead to long queues and frustrating wait times. Our study is directly inspired by by the real-world context of the Makati campus, which utilizes a segmented elevator system for its diverse users like students, professors, and staff. Our primary motivation is to quantify the performance of these existing systems and explore the potential optimizations to ensure fast, fair, and efficient mobility for everyone on campus. This brings us to our problem statement. The current issue we're addressing is the hypothesis that Mapu's existing elevator configuration might not be meeting demand as efficiently as possible, potentially leading to longer wait times and frustrating bottlenecks for users. A significant challenge is the lack of quantified performance data. We don't have clear exact metrics on how this specific system performs under varying user traffic, and the time-sensitive patterns unique to an academic schedule. Therefore, our core challenge is to objectively evaluate the capacity and the current allocation strategy of Mapu's elevated system to ensure that it can effectively serve the dynamic needs of a mid-sized academic institution. To address this challenge, our main objective is to optimize elevator allocation and minimize wait times. We aim to achieve this by simulating various user behaviors and demand scenarios using a powerful tool called agent-based modeling, or ABM for short. Our scope for this research involves modeling the distinct behaviors and needs of students, professors, staff, and maintenance personnel as individual agents, evaluating on how the current system handles typical peak traffic conditions and identifies existing bottlenecks. And importantly, our focus is to specifically focus on the Mapua Makati campus building, encompassing its 7 floors and 2 basement levels with its unique segmented elevator system. Ultimately, our key goal is to test the system's performance under different conditions and identify concrete areas for optimization in both its capacity and existing resource allocation strategies. Now let's move on to the literature review where we contextualize the study within existing research or knowledge. We explored several key areas, starting with agent-based modeling in elevator systems. EBM is a powerful paradigm because it simulates individual passengers in elevator cars as an autonomous agent, each with their, each with their own simple decision rules, of course. From these individual interactions, system-level performance metrics like wait times and elevator utilization emerges. This approach has been proven highly effective in various applications for high-rise buildings in examples such as Chang et al.'s research, in which they investigated off-peak operations in a 21-story tower building, notably identifying a critical arrival rate where wait times drastically increase. Locally, Batasalam et al.'s research applied ABM to a Manila high-rise, achieving significant reduction in 23% in round-trip times, 40% in waiting times, done through optimized static car allocation, and peak hour trip deactivation strategies. Beyond routine operations, ABM has been used for emergency evacuation planning, as shown by Chen et al.'s research, who demonstrated optimized dispatching could reduce egress by 30 to 40%. More recently, Garby et al.'s research developed intelligent ABM-controlled elevators, showing improvements in response time, multi-car capacity, and even energy efficiency during high-traffic scenarios. While this body of work is extensive, we have identified crucial gaps in existing research that our study aims to address. Firstly, there's limited focus on mixed-user academic settings, while most studies concentrate on commercial high-rise offices or emergency scenarios, rather than the unique role-based elevator allocation found in universities. Secondly, the existing models often overlook variable demand conditions specific to academic schedules like fluctuating class times and intense peak traffic hours, which profoundly affect elevator performance. Lastly, there is insufficient attention to real-world floor configurations and access restrictions. Few models fully account for specific ro- role-specific access to elevators and specific floor layouts, which are critical in environments like Mapua University. These gaps directly led to our justification for choosing an agent-based modeling approach. ABM is tailored to real-world dynamics. It excels at capturing the complex, heterogeneous behavior of individual passengers, including their varying arrival times, destinations, and even patience levels, reflecting to the true variability in elevator usage. It's highly suitable for mixed-use environments. Our ABM model can precisely simulate the role-based elevator allocation at Mapua, students, professors, and staff, primarily, and to account for specific access restrictions like those to basement floors. By simulating Mapua Makati campus's configuration, our study directly addresses the key gaps in integration of real-world elevator allocation, user-specific behaviors, and time-sensitive demands to comprehensively evaluate system performance. Ultimately, this approach will provide actionable insights for campus management, offering data-driven recommendations to optimize elevator allocation strategies and identify specific system bottlenecks unique to an academic institution. I'll be passing it over to my groupmate Louiese Gabrielle Nase for the methods and system design.
Hey, how's it going? Luis here, and I'm going to discuss first the modeling approach as the first part of our methodology. So, the approach we used is agent based modeling, or ABM for short. So, why did we use ABM? Two reasons. Okay, it captures decentralized decision making and it reviews emergent behaviors like congestion and elevator overuse. So the agents in the simulation, we have person agents, which are students, teachers, and staff. So their behaviors are the following, which is call elevators, wait for the elevators to arrive, ride elevators, and exit elevators. And then we have also the elevator agent. So its behaviors are respond to calls, move, move amidst floors, and load and unload passengers. The interaction logic is based on access rights, destination, and load handling. And the justification for this approach is ABM better handles complexity versus static, analytical, or equation based models. Next up is we have assumptions and simplifications. So we are going to divide this between category and then the assumption. First one is spawning category. So the spawning is random and floor based. The next one is access logic. We have role based preferences. Button press behavior category, we have the assumption of instant upon appearance. And then the travel simplification category, we have no door time penalties. Right? That's what we have. And then the capacity category, we have fixed and overflow wait. So the passenger that cannot enter the elevator should wait. And then the simulation time, we have 3,600 seconds per run. That's about an hour. And then we have the tools and technologies we used in this project. We have first one is the Python 3.12. Its purpose is it is the simulation engine and the logic. It is the language we have used. And then Takinter. It is a graphical UI for elevator and agent visualization, which is a part of Python. We have matplotlib, which is a library, a real time per which generates real time performance graphs to visualize data. Then we have NumPy, which is used another library, of course, which is used for randomness, math, and numerical operations. And then lastly, we have the time module in Python as well, which tracks and simulates time progression. And then we move on to data collection. So the purpose of data collection is to establish a realistic basis for validating the simulation. And we have captured typical elevator demand patterns and user distributions, student, professor, and staff during regular school operations. So the methodology is we have manual observational data collected at Mapua University campus, and each floor observed individually for 10 minutes, recording people waiting and their roles. They could be a student, they could be a professor, or they could be a school staff. And then the role of collected data in validation is simulation is synthetic, agents generated by randomized logic and not direct real-world logs. Manual data used post-simulation for crucial comparisons. So we have cross. It is used to cross-check simulated wait times and role-based agent distributions, and compare actual elevator demand profiles against model outputs, and assess if simulation reflects observed phenomena, which includes the following: congestion, idle times, and underutilization of elevators. And the data collected in the manual observation will contribute to confidence. This real world reference, though limited, provides qualitative confidence in the simulation's ability to approximate real world actual behavior elevator system in an academic environment. Now, model design. We have the following agent definitions. Again, person agent attributes is role. They could be student, teacher, or staff, current floor, destination floor, and wait time. And then for the behavior of person agent, it waits for eligible elevator, boards if space permits, and then exits at destination. Next agent is the elevator agent, as said before. The following attributes they have is shaft ID, current floor, direction, could be up or down, and then the capacity. And assigned roles, of course. So the interaction logic is role-based access rules. We have students is strictly limited to elevators 1 to 3. Teachers prefers elevator 4 and 5 but can use other elevators if preferred, are busy or wait times are too long. And then the staff prefers elevator 6 but can use any other elevator when necessary. Okay. Elevator dispatch logic is elevators follow a nearest request logic and then dynamically adjusting direction to fulfill queued calls within their service zones and role assignments. That is our model design. Lastly, for our model design, we have the elevator logic pseudocode. So this following code means elevator actions and agent actions. First, let's start with the elevator actions per elevator. It unloads passengers who have reached their destination floor and load agents waiting on the current floor only if their role is allowed on that elevator and only if there's an available capacity. If there are pending requests or onboard passengers, it determines the nearest requested floor and move one step toward that floor. And if that elevator is idle, which means no tasks or passengers, the elevator remains in place. Then the agent actions per agent, if not yet boarded, it increase wait time. And if assigned elevator is unavailable for too long, try to use a fallback elevator if allowed by its role again. For the chapter 4, we have the simulation design. And for the very first part of this chapter, we have the simulation overview. Our project simulates Mapua Makati's real elevator system with 6 elevator shafts and role-based access. Elevator 1 to elevator 3, we have students only, and elevator 4 and 5, we have professors preferred this elevator shafts, and elevator 6 is staff preferred elevator. So we simulate 3,600 seconds or an hour of elevator operation, and it is built with Python 3.12 language and Takinter for GUI and Matplotlib for real-time analytics. For the next part, we have these following simulation parameters. So we have the symbol column, meaning column, default value column, and the rationale or notes column. First symbol, we have capital T, which means virtual runtime per experiment. Its default value is 3,600 seconds. So it matches one academic hour block plus turnover time. The next symbol, we have the lambda, which means the mean call rate for Poisson, and its default value is 0.10 calls. Uh, and it is chosen to reflect a moderate class change peak, and it is varied in stress test. We have the capital C, which means elevator capacity. Its default value is 19 people. It is the conservative value from manufacturer's specification sheets. We have the small v, which means travel speed. Its default value is one floor step. One model step is equal to one real world second. Then we have the W sub minimum minus W sub max, which means idle wait before forced dispatch. Its default value is 3 to 8 seconds uniform. It captures button mashing impatience without micromanaging door dwell. In the last symbol, we have the delta, which is the sampling interval for metrics. Its default value is 10 steps and keeps data volume manageable while preserving trends. And now for this next part, we are going to discuss input data and sources. It has four columns: parameter, value or values, role in model, and the data source or status. First parameter is elevator capacity C. Its value is 15 people, and the role in model is it is the car load limit. Our data source for this one is Mapua elevator information. The next parameter is travel speed V. Its default value is one floor per second. Its role in model is floor to floor time, and its data source is it is predefined constant and no measured data. The third parameter is idle depart timer W. Its value is uniform 3 seconds to 8 seconds. The role is door dwell logic for the model, and its data source or status is assumed typical lobby clear practice. Fourth parameter is role mix by shaft. The value is 90% students for elevators 1 to elevator 5, and then 100% staff for elevator 6. Its role in the model is it is the access segregation. Its status or data source is policy assumption and no empirical log. And then the fifth parameter is arrival rate lambda, which is 0.05 or 0.10 or 0.25 calls per second. Its role in model is factor varied in study. Its data source or status is it is the scenario design choice. And then the last parameter is horizon T. Its value is 3,600 seconds baseline, and the role in model is observation window. The data source or the status is it is the modeling choice. For the next part, we have the experimental scenarios. It has three columns, as you can see. The first one is scenario column, second is purpose, and then the third one is key changes from baseline. Baseline scenario, its purpose is to establish reference performance. The key changes from the baseline is lambda is equal to 0.10 calls per second, and then time is equal to 3,600 seconds. Light load scenario, its purpose is demonstrate near free flow operation. Lambda is equal to 0.05 calls per second. That is the key change from the baseline. Next scenario is the heavy load scenario. We have the purpose is to locate saturation point, and then the key change from the baseline is that lambda is equal to 0.25 calls per second. And then the fourth scenario is the extended horizon. Its purpose is to show steady state convergence, where the key change is time is equal to 7,200 seconds and lambda is fixed at baseline. And the last part we have to discuss for the simulation design, we have the verification and validation. Code verification is where unit tests ensured legal floor access and correct passenger counts, and then the assertions prevented overloading. We have analytical benchmarking, which compared wait times at light traffic where lambda is less than or equal to 0.05 to standards M/M/6 queuing models. We also have the sensitivity testing, which includes varying lambda capacity and weight thresholds represented by capital W as a parameter, and showed expected performance trends, which is wait time increases as lambda increases or the calls increases. And then we have the performance testing where the simulation completed in under 60 seconds or 60 times real time on a standard octa-core laptop, making it usable for live demonstrations.
So now we have our elevator simulation created using Python, and if we run it we can see this screen. So on the left side, this represents the Mapua building. It has 8 floors and 2 basements. So we have 6 elevators. 2 are dedicated for teachers and staff. 3 are for students, and 6 are for contractors and staff only. So for elevator 1, it can go from basement 2 to 8th floor. For elevator 2 to 5, can only go from ground floor to 7th floor. And elevator 6 also goes from basement 2 to 8th floor. So we have our basic dashboard here. We have the duration as the buttons and speed of the simulation. So now let us try to simulate for just a moment. So as we can see, we have here our elevators moving. The green represents the students, the red one represents the staff, and the blue one represents the teacher. So in these 3 elevators, there is still a possibility where teachers and staff can actually ride this elevator. So stop. Let's now proceed to our analytics. We have here our average wait time over queue length, and the second graph is for the elevator utilization, and next is the fulfilled and demand graph. So we have here our analytics. We have the wait time distribution, elevator utilization, the queue analysis, the throughput analysis, system efficiency, load factor analysis, demand versus supply of the elevators, service time analysis, energy consumption analysis, and movement patterns of the elevator. So that's all for our simulation.
So moving on, we have our results and discussion. Here we summarize our key findings on system responsiveness, role-based weight disparities, elevator utilization and throughput patterns, and model validation against campus observations. So details of each figure will follow. So let's start with the figure 5.1. Over the 3,600 second run, average wait time climbs steadily from near zero to roughly 15 seconds, even as the queue length oscillates between about 5 and 30 passengers, illustrating intermittent congestion. Meanwhile, the utilization to request ratio surges from 0.2 to above 0.9 within the first few hundred seconds before plateauing near 1.0. And cumulative fulfilled requests grow almost linearly to about 1,400, with unmet demand remaining negligible. So together indicating that the elevator system rapidly adapts and consistently meets passenger arrivals. Next, we have our figure 5.2 and 5.3. So for figure 5.2, the staff experience almost waits under 20 seconds, teacher under 40 seconds, and students display a long tail up to 150 seconds. So while box plus show that E2 to E5, which is elevator 2 to 5, encounter greater weight variability and outliers compared to the more stable elevator 1 and elevator 6. The average wait time rises smoothly to about 12 seconds by the end of the simulation. And summary statistics report mean waits of 5.74 seconds for the staff, 10.60 seconds for the teachers, and 15.41 seconds for students. So with standard deviations of 15.90 seconds, 24.74 seconds, and 21.89 seconds respectively. Moving on to figure 5.3. This shows that all 6 elevators maintain utilization rates near 1 over the 3,600 second run, dipping only briefly on E6 and E2 with average utilizations of 0.981 and 0.998. BC step counts revealed that E1 and E6 shoulder the most of workload, while E2 to E5 each record under 217 BC ticks. So the accompanying table confirms these high efficiencies alongside with the uneven distribution of service load. Next, figure 5.4 and 5.5. Figure 5.4 tracks queue dynamics across elevators. The time series, total queue length oscillating between 0 and 30 throughout the run. So reflecting intermittent congestion, the bar chart reports average queue lengths of just 0.08 for E1 and 0.03 for E6 versus a roughly 4.1 to 5.1 for E3 to 5. So and 1.86 for E2. So the histogram reveals that the most time steps have 0 queued requests, with smaller peaks at lengths of 5 to 10, and the summary table confirms that these findings show minimal mean and maxes for E1 and E6, moderate levels on E2, and the highest queue burdens on E3 to E5. Next, for figure 5.5, the throughput rises almost linearly to about 1,650 completed trips over 3,600 seconds. So with E1 and E6 against serving the fewest passengers per interval versus roughly to 330 to 336 for E3 to E5. Total trip counts mirror this pattern. E1 leads with 83 trips and E6 follows at 71, while E2 to E5 each log around 41 to 42 trips, resulting in per interval efficiency of 3.25% of E1, 6.24% for E2, and roughly 7.95 for E3 to E5 compared to only 1.41% for E6. Moving on to our next two figures. For figure 5.6, the system efficiently climbs swiftly from 0.2 to 0.99 within the first few hundred seconds, and then holds steady near at 1.0. So per elevator, service rates range from 0.007 to 0.02 calls per tick. So highest on E1, 0.02, and lowest on E2 and E3 for 0.007. The response time distribution skews heavily towards sub 50 second service events with a long tail up to 1000 seconds. Overall, 1,636 passengers are served in 1,686 service events, yielding an average of system utilization of 0.993 across all 6 cars. Moving on, figure 5.7 shows that individual load factors fluctuate widely, but E3 to E5 consistently operate near full capacity, while E1 and E6 mostly remain underutilized. So average load factors are 0.252 for E1, 0.653 for E2, and about 0.85 for E3 to 5 before dropping to 0.213 for E6. The distribution shows most time steps at zero load for E1 and E6 and peaks at full load for E3 to 5, and the statistics table confirms zero instances above 80% on E1 and E6 versus 1,588 to 2,663 such instances on E2
Now
to
let's move
E5.
on to the figure 5.8. Demand supply across each elevator. During the initial 500 seconds, elevator capacity exceeds queued requests, but as this simulation progresses, supply light tightens as elevator remains constantly active. Demand fluctuates between 5 and 25 calls with no runaway peaks, indicating that the system can absorb typical traffic, but in its buffer space narrows down under continuous use. When broken down by shaft, we observe that elevators 3 to 5 and elevators 1 to 2 experience peak queue lengths of 10 passengers, while stop elevator E6 peaks at just 1. This reveals that inner shafts bear the bulk of demand, creating localized congestion, while elevator 6 remains underused even during peak times. So a utilization versus queue scatter plot confirms that the dispatch system is responsive. Whenever a queue forms, elevator utilization jumps to 100%, proving that the system doesn't leave passengers waiting unnecessarily when capacity is available. In aggregate, the system handles 1,636 served events with an average queue length of 2.77 and a demand to supply ratio of just 0.031. This shows excellent overall capacity but highlights bottlenecks on specific shops. Now, moving on to 5.9, the average service time, how long it takes elevator to complete trips. Moving averages reveal that elevator 2 to 5 periodically spike above 250 seconds, indicating long multi-stop trips or high passenger loads. In contrast, elevator 1 has consistently short service times, around just 50 to 100 seconds, and elevator 6 is moderately loaded. Uh, on average, elevator 3 and 2 had the longest service durations of 135 plus seconds, while elevator 1 remained the most efficient of 50 seconds. This aligns with their usage roles. Elevator 3 handles heavy student traffic, and elevator 1 may serve shorter basement ground trips. These diagrams of service duration shows a long skewed tail. Most trips are short, but outliers can take up to 1,000 seconds. These rare long trips increase system variability, especially on high demand shafts. Moving on to figure 5.10, the energy consumption graphs, and 5.11, the movement and trip pattern graphs, we explore the physical workload of the elevator fleet using both energy usage and the vertical travel as proxies for system activity. In figure 5.10, we use energy as a proxy for vertical movement. The time series plot shows nearly continuous elevator energy usage after the first few minutes, indicating sustained activity across all shafts. Cumulative energy data reveals that elevator 1 through elevator 6 consumed almost identical total energy, suggesting balanced movement even though passenger loads varied. The histogram shows that most energy samples are 1, which means active movement, with very few zeros, which mean idle. Confirming the fleet's high operational duty cycle, the average probability of being active ranges from 0.981 of elevator 6 to 0.998 of elevator 1, supporting the earlier conclusion that that the system is highly responsive and rarely idle. In figure 5.11, we examine elevator movement patterns and trip distances. The floor heat map reveals that basement 2 and the eighth floor are the most frequently visited in our synthetic simulation, uh, and uh, likely reflecting administrative activity or class density. Floor 2 through 5 also shows moderate usage in terms of movement steps. E1 and E6 record the highest totals, which is 643 and 497 steps, indicating they handle more vertical traffic. E1 mostly for basement runs and E6 for upper floor transport. Meanwhile, elevator 2 to elevator 5 handle fewer movement events consistent with their shorter, less frequent trips. The histogram of floor distances shows that most trips span just 1 to 3 floors, confirming that short haul elevator dominates. However, a small number of long distance trips inflate service times and energy consumption, especially for shared or overflow shafts. Now that we have interpreted all our graphs, we now move on to section 5.2, which is our sensitivity analysis, where we calculate how the system behaves under varying passenger arrival. In this section, we examined how changes in the passenger arrival rate, noted as lambda, affect system performance. We tested three demand scenarios, which is light, lambda is equals to 0.05, baseline, lambda is equals to 0.10, and heavy, lambda is equals to 0.25, while keeping all other parameters constant. And our results showed that passenger throughput increases nearly linearly with lambda, even under heavy load. The system maintained over 99% utilization, indicating high efficiency. However, wait times did not scale linearly. The student mean wait times tripled from light to baseline traffic and increased further under heavy load. Queue dynamics also became more unequal. Under baseline, Professor Car Elevator 5 had the longest queues, but under heavy load, congested shifted to student and overflow cars, elevator 3 and elevator 4. Despite this, staff car elevator 6 remained largely underused. Finally, we noticed a service imbalance. Elevator 3 to elevator 5 handled over 60% of trips under heavy traffic, while elevator 1 and 2 stayed relatively idle. This shows that role-based access, though effective, can cause load clustering in central shafts. These results suggest a critical lambda threshold near 0.10 where fairness breaks down. To fix this, we recommend temporarily allowing students onto staff or professor elevators during peak hours and improving the dispatch logic to account for lobby congestion rather than just nearest car rules or the now moving on to section 5.3, which is the comparison of gathered outcomes with benchmarks or in benchmarks. We collected 10-minute manual field data from each floor of Mapua Makati to compare real weight patterns with our simulation output. And we can say that the simulation correctly predicted the ordering of wait times, with students waiting the most and staff the least, mirroring campus behavior. However, the model overestimated the student wait times by about 1.5 to 2 times. The simulation produced a mean of 15.4 seconds, while observation suggested about 9 seconds. Still, this is within acceptable design benchmarks for academic elevators, which is 20 to 32 seconds. And of course, we identified the three reasons for this gap. Our field data was limited, a single 10-minute window, possibly during off peak time, And the simulation uses a constant arrival rate, which is the Poisson distribution, which doesn't reflect real class change burst. And of course, our small sample sizes, especially for professor and staff, which caused statistical noise. And of course, to improve this alignment, we propose calibrating lambda using real arrival logs, modeling demand peaks around class schedules, and conducting multiple validation runs using Monte Carlo sampling. With these adjustments, we expect the model to match real-world averages more closely and support better operational planning.
To conclude our project, our simulation was able to successfully replicate the elevator system at Mapua University Makati campus using agent-based modeling. The system achieved impressive overall performance with over 97% of passenger requests fulfilled and a fleet utilization rate of 99.3%. This indicates that the role-based dispatch logic and elevator allocation are generally effective under load conditions. However, when we look deeper into the user experience, we see emerging inefficiencies. Students experience the longest average wait time at around 15.4 seconds, followed by teachers and staff. This is largely due to the congestion in student designated elevators, which are E3 to E5 elevators, which carried the bulk of the traffic. Meanwhile, other elevators like E1 and E6 were underutilized despite being active. This imbalance suggests while the system works, it does so at the cost of fairness and efficiency, especially during peak hours. Overall, our model revealed that the current configuration is functional but not optimal, particularly for high volume groups like us students. Moving on is the limitations of our simulation. First of all, our model relied on a synthetic agent generation using a Poisson process, which assumes a constant arrival rate. In reality, elevator demand at school fluctuates, especially during class changes. Second, while we collected real-world validation data, it was limited to a 10-minute observation window per floor, making it difficult to generalize for roles like faculty or staff who appear less frequently. Third, we made a few simplifications for the sake of real-time performance. Elevators had instant call response, no door delay or boarding lag was considered, and travel speed were constant. These assumptions slightly reduce the realism of our simulation, especially in high-density scenarios. But despite these limitations, the simulation still aligns closely with the observed campus patterns. Lastly, to improve the system and future versions of the simulation, we recommend several next steps. First, we suggest integrating real-world usage logs like swipe card data or time-stamped elevator calls to better reflect actual traffic patterns. Second, the school could consider adaptive access rules, for example, temporarily letting students use the E6 elevator during class change hours. This would help distribute the load more evenly. Third, the simulation should simulate time of day surges, especially during peak periods like breaks or dismissals. Fourth, we can also explore dynamic dispatch strategies where idle elevators are assigned based on real-time queue length rather than just proximity. Lastly, we recommend expanding data collection with longer and more frequent observation windows to improve validation, especially for low-frequency users like professors and staffs. And all in all, this simulation proves that agent-based modeling can be a powerful decision support tool for managing shared resources like elevators. With further tuning, it can support both campus planning and classroom teaching.